Alright, so in this video I'm gonna be explaining another important article on model editing with the title Graph Edit Networks. This paper in 2021 in ICLR. While graph neural networks have made impressive progress in classification and regression, few approaches to date perform time series prediction on graphs, and those that do are mostly limited to edge changes. We suggest that graph edits are a more natural interface for graph-to-graph learning. In particular, graph edits are general enough to describe any graph-to-graph change. Not only edge changes, they are sparse, making them easier to understand for humans and more efficient computationally. And they are local, avoiding the need for pooling layers in graph neural networks. In this paper, we propose a novel output layer, a graph edit network, which takes node embeddings as input and generates a sequence of graph edits that transform the input graph to the output graph. We proved that a mapping between the node sets of two graphs is sufficient to construct training data for a graph edit network, and that an optimal mapping yields edit scripts that are almost as short as the graph edit distance between the graphs. So we connect graph neural network to these edit distances by just a linear output layer that maps node embeddings to graph edits. So this is a representation that we use because graph neural network compute representations of nodes in a graph by just aggregating information of neighbor nodes. And after that, we have another thing, combination. For example, here we call it merge. And merge it with the information of that node itself, and the neighbors. And graph generators are interesting as well. Multiple works in recent years have proposed to generate graphs. For example, link prediction is complementary to graph generation. It assumes a constant number of nodes but changing connectivity between them. And time series prediction, which is the motivation of this paper, is that only very few works to date have addressed the most general case of time series of graphs, where both nodes and edges are permitted to change. At each instance of time, if you just change, for example, we have a graph, at each instant of time, you just change one node or one edges, it takes a long time to generate the graph. So to obtain the corresponding graph, a multi-layer perceptron is used to compute adjacency matrix and node features from predicted embeddings. So the basis for our approach are graph edits, which are functions that describe changes in graph. So we first define an attributed directed graph as a triple, and V is a finite set of node indices, E is just edges. So we define a graph edit delta. So we consider graph edits, namely node deletions, which delete i's node from a graph, node replacement, which set attribute of node I to x, node insertions, which add a new node with attribute x, edge deletions. There are many kinds of graph edits, but you can always compose them like this. First we do, for example, in the first time we do node deletion, then we do what? at each instant of time. It can be a combination of them. So what is this graph edit networks? You have this original, you give it to this, we get node scores as well as edge scores. Traditionally, we get node scores. For example, in graph pooling, we say which node is important to be kept in the next hierarchical pooling layer, but that's not sufficient. Here in graph edit, we are also caring about edge score. That's interesting. So we combine this information and then we get the predicted graph. So our proposed is just a linear layer to compute edit scores that express which nodes and edges should be deleted, inserted, or relabeled. As simple as this. So we go from scores to edits. We translate these scores into edits. And this is the algorithm that they present. So in the first case steps of a teaching signal, we have a classification loss for decision of inserting a node, plus a loss of vanishing deviations between predicted attributes and desired attributes. And once training is complete, we wish to use our gen for inference. So given a previously unseen graph G sub t, we want to know its successor at next instance of time, what happens to the graph. So this is some theoretical work as well to support their very simple algorithm, very interesting algorithm. But of course it has many limitations that when I talk about another playlist, graph representation, you will see that why it's not sufficient to just do these things. There are many other, after reading 200 papers about graph neural network graph representation, I noticed that there are 9 fundamental problems that we should care, such as over squashing, over smoothing, positional encoding, and so those are very important to make any decision, hierarchical modeling decision, anything. Our motivation should be based on these 9 fundamental problems that I've discovered among more than 200 important articles. So this is their algorithm.